Okay, I'm sorry this is so late. Grading took a lot longer than I thought it would this weekend, which is always the case. But I wanted to do a little bit of instruction using the Energy Study Guide answer key as the material. So let's take a look at that Energy Study Guide and go over some of those answers together. Okay, the birds have currently calmed down a little bit, so I'm going to try to sneak this slide in recording here before they start screaming again. So we've got this first learning target. It's all about gravitational potential energy. GPE, again, has to do with the height. So we don't care about the whole pathway, right? So this whole pathway here is significantly longer than 0.75 meters. But the height it goes up is the 0.75 meters. I didn't give myself enough room to work with there. Let's go 0.75 meters in height, and then you just plug it into the equation. So you got mass times gravity times height, and you multiply them together. So it's really that simple. The math for energy is not the most challenging thing ever. The second question is fundamentally flawed. It's a bad question. I didn't write this particular worksheet, and this is why I usually write my own worksheets from scratch, is because sometimes other teachers just get it wrong, unfortunately. And this is the case. Velocity doesn't work like this. In order to use this velocity equals distance over time equation that I used, that needs to be a constant velocity, and obviously this is not a constant velocity. It starts at 0 and then it reaches its maximum velocity down here. So you would solve this equation a very different way than this. But because the goal of this was to practice the kinetic energy equation, I pretended that velocity worked this way just to get a number. So this question is flawed. It won't be on the test or anything like that because it's a bad question. But basically what I want to show you is kinetic energy is 1/2 mv squared. So you take 1/2 times mass times the square of velocity, and you get your answer. So again, you just plug the numbers into the equation. That's what I'm trying to show you here. But please note that this question, this situation is flawed. So if you're like, wait, I feel like it doesn't work that way, you were right. So I wanted to go over that. But basically, mathematically speaking, it's as simple as plugging your numbers into the equation and solving. Again, if you're doing it on a calculator, do your v squared first. That way you follow order of operations. So you would plug in 3.3 squared or 3.3 times 3.3 first, then multiply by 1.75, and then divide by 2. And that's how you would get your final answer. The birdies are being very nice and letting me talk right now. Hopefully that continues. It helps. We've got Star Wars on in the background. So I think the birds are watching Star Wars. So we'll keep them distracted. But let's take a look at these last two learning targets. These are really the ones I wanted to focus on. So learning target number 3 here, you can calculate GPE and kinetic energy from each other. So you have this concept of total energy here. So let's say it's a roller coaster, right? Your roller coaster gets dragged up to the top of its tall hill by the chain, and then it has some GPE. And that's how much energy it has to work with, right? It has a certain amount of energy at this first hill, right? The motor or the engine or the chain, whatever, gave it its energy. Then it has that total amount of energy. Once it has that total amount of energy at the top of that first hill, it's mostly potential. It's not really moving at all yet. It's barely moving. Most of that energy comes from gravity. And then as the cart goes down the hill, that potential energy turns into kinetic energy as it speeds up. But we don't create any more energy. We're just turning that potential energy into kinetic energy. So the maximum speed, the maximum kinetic energy in this case, maximum kinetic energy is all going to come from that gravitational potential energy. So you can see that I've set this equation here where the max kinetic energy will be the same as the max gravitational potential energy. It's just that now we've turned that potential energy all into kinetic with the cart moving. So kinetic energy max happens at the bottom of the roller coaster when it's moving fast. So let's say we got a roller coaster here. Kinetic energy max happens here at the bottom when it's moving its fastest. And then potential energy max happens here at the top when gravity has the most room to work with there. And then as it goes down the hill, gravity converts that potential energy into the kinetic energy. So to calculate the maximum kinetic energy from a height and a mass, you just have to recognize that the maximum kinetic energy at this point will be equal to the maximum potential energy at this point, because that's where that energy came from, is gravity. So that's a key one that I wanted to point out there. And then exact same train of thought here, except now we take that kinetic energy at the bottom, sorry, that kinetic energy we just calculated at the bottom here. So we take this kinetic energy that we calculated, the maximum kinetic energy, and we solve for V, right? So this equation, this formula, is just the 1/2 mv squared formula rearranged to solve for V. So this is the kinetic energy formula here, but we solve for V, we solve for velocity. So to get the max speed, first you need to find the maximum kinetic energy, the same way we did in the previous problem, right? mgh. And then we solve for velocity, or speed, right? Because we don't know the direction. Energy doesn't tell us direction. So this will just give us a speed. I should have said speed here, not velocity. Sorry about that. I'm just so used to saying velocity in physics. And kinetic energy is one of the times where you are talking about speed, not direction. So same thing as the previous problem. We just took it one step further and actually solved for velocity, so we know the maximum speed of this roller coaster. And that's pretty much all the new stuff. Everything else is the exact same as the notes. And honestly, this isn't anything new. It just takes what we learned in the notes, and now you kind of have to think about it a little bit further and think, where is the energy coming from in a roller coaster? Right? It starts in the beginning, that energy starts up here, and then in the end, right, it's converted to kinetic energy, but all of that kinetic energy came from that gravity right at the beginning. That's the source of the speed. So in order to find the maximum kinetic energy or the maximum speed, you first need to know how much potential energy it started with and go from there. In terms of the problems, it's very straightforward problems here, and really this is how energy works for the most part. I didn't give you any problems where you had to subtract to find the height, so that is the one thing that I showed you in the notes that we didn't really practice here at this practice, so keep that in mind, that, like, again, if we have a roller coaster like this, but the ground is down here, right, it never actually reaches all the way down to the ground, then the potential energy only factors in the part that you actually use. So you would ignore this part down here because that's not actually part of your problem. So we didn't practice that in this one, which is why I pointed it out again, because that is still a thing. But other than that, it's exactly as easy as this answer key makes it look. You take your equation, you either take your kinetic energy equation if that's the one you want, or you take your potential energy equation if that's the one you want, and you plug in the numbers. Or if you want a velocity, you take the kinetic energy equation, but you solve for V. Or you can solve for height, right? So you can solve for height using the potential energy equation right here. If you divide by m and g, you can solve for a height that way. So it's just algebra. You find the variable you want to solve for, and you solve for it using the equations. There's nothing fancy here at all. Very straightforward stuff. So again, if you're not good at algebra, that's totally fine. You still get partial credit by setting it up correctly. So for partial credit, I'd be looking for something like this that shows you identified your equation correctly. Then if you make a math mistake, you won't lose too many points there. However, if you just write down a number and it's wrong, you get 0 points because I can't see your thinking. So please show me your equations. But really, it's that simple. You write down the equation, you plug in the numbers, solve for the number you want. And that's all there is to it. And it looks like we're going to keep this video to under 10 minutes, which is great. Well, around 10 minutes. So I'm going to stop wasting time here and dive right into it. Friction and how friction impacts energy. Friction takes kinetic energy that's useful. So like a bowling ball rolling down the alley, that's what we would call bulk kinetic energy, where a large object in like a real life-size object, not a molecule or something like that. An actual physical object is moving. That's what we call bulk kinetic energy, because it's not just one molecule or something, it's the whole object, all the trillions of molecules in it, all moving together in the same direction. So that's the regular kinetic energy we're used to, like a bowling ball or a roller coaster. But there are other kinds of kinetic energy. You may remember from the notes, I said anytime something's moving, that's a type of kinetic energy. And so there's two types of kinetic energy that friction really plays into. The one we're going to focus on is called thermal, and you'll see that here in number 2. Thermal kinetic energy is heat. So heat is created by the random vibrations of particles, the random vibrations of atoms and molecules, and even subatomic particles vibrate with heat as well. And so when objects rub together, I'm going to use my hands here again to demonstrate, rubbing my hands together, you can feel that heat on your hand as the kinetic energy from your hands is being kind of stolen by friction and used to heat up the molecules on the surface. So if we were to zoom in on our hands and see the molecules, it would look more like this. So our hands feel nice and smooth, and depending on how dirty they are, they might be pretty smooth, but everything when you zoom in on the molecules is not perfectly smooth. It has little bumps and ridges and imperfections just like this. And those bumps and ridges and imperfections, they rub against each other as two objects slide together. So like this with your hands again. On the molecular level, that's what's happening. So as those molecules and ridges and everything collide and bump into each other and get stuck and unstuck, that causes those molecules to bounce around and create heat, thermal energy. So that energy from your motion, from the bowling ball or the roller coaster or your hands or whatever, is being stolen by friction to cause those molecules to bounce around and generate heat. So friction generates heat. Sorry, I'm getting notifications there. And it also generates sound. You can hear that, right? Again, I'm going to demonstrate with my hands, rubbing my hands together. You can hear that sound. So sound waves moving through the air, another form of kinetic energy. Sound waves are pressure waves, and they definitely carry energy with them. Most traditional explosives that aren't nuclear, like C4 and stuff like that, they work very similar to sound, just very, 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 very high pressure waves of energy. Right? So definitely sound is a form of kinetic energy as well. So friction will take your kinetic energy of things moving, and it will convert it into sound energy and heat energy, and that's how friction stops things and slows things down. So you can calculate that just like this. If you know how much energy you started with, how much potential energy you started with, and if you know how much kinetic energy something has at the end, so say a child sliding down a slide, and at the start it has 1,000 joules of potential energy, at the end it has 900 joules of kinetic energy. Where did that extra 100 joules go? It went into the sound and the heat because of friction. So friction created 100 joules worth of heat and sound energy, and because of that, the kid sliding down the slide lost 100 joules of kinetic energy. So if we were to do our energy lab, that's exactly what we would be doing. Unfortunately, I don't think that's going to happen just with the timing of things. So we'll successfully complete 2 labs this year with the friction lab and the science fair. But once again, unfortunately, I didn't get my 3rd lab in because of some crazy situation. I always tend to teach physics during the semesters where some situation occurs that doesn't let me get my last lab done, and that seems to have happened again. But just make sure, again, why would this sandy thing down here have the most friction? It's because the sand creates a rougher surface. So as the bowling ball's trying to slide, it crashes more into that sand. That sand creates a more bumpy, rigid surface for the molecules on the bowling ball to rub against, and the bowling ball will start to lose its energy to heat and sound more quickly that way than on the smooth lane. So That's what it's all about for friction, is the rubbing together, and the molecules themselves steal the energy as they heat up, and sound waves also create energy. So conservation of energy is still followed. The universe has the same amount of energy. It's just, instead of the energy being carried by the bowling ball, it's now being wasted as heat and sound. So that's what happens. And thank you guys for following along. No exit ticket today or anything like that because I'm behind schedule. I just wanted to have this video available to answer your questions. And if it didn't answer your questions, please let me know.